Well, if we are ready, I see people coming and going. It's my pleasure to introduce the next plenary speaker, Professor Irvine, and the presentation will be about electrochemical CO2 conversion. Professor? Just to share.
Yes. Well, just checking online.
Okay, thank you very much. I think I'm the only UK person here, which is not a good thing, but at least good for me, I'm here.
Professor Irvine, sorry, because the people online, please keep closer. Sorry for that.
Private. Better than it was this morning in the other room. Yeah, so it's good to be here, and I'm going to tell you a bit of some of our work on conversion CO2 and using solid oxide electrolysis in particular. Start off looking a little bit about methane and oxide after an overview, then some CO2 electrolysis, and we'll talk about X-solution, biogas, and finally about our ongoing work in olefins on co-ionic conductors. On the slide, you can see a view that's from my front room, and you can see it. Our sheep are well ordered and heading off in the morning. Over here, you actually have a CO2 cement factory on the other side of the fourth, and about a megawatt of wind off to the left as well. No, a gigawatt, 700 megawatts. So on the fourth. So every day I see the energy problems and solutions. So in addressing climate change, we need efficiency, we need renewables, and we need change, which means we don't need so much stuff, and we don't need to spend so much money on cheap clothes, wasting money on gadgets. The internet, of course, is a sore point. If we didn't have AI, probably is now using 8% of our global energy. Is that actually? Are you ever going to get that back from digital? Remove. We can sequester CO2 underground. I much prefer utilizing it. But also, nature is very important. Forestry, increasing carbon in the soils, and you can see that we keep sheep and cows at home. We're very low intensive, pretty much organic, and that our soil has got a lot more carbon in it than our neighbours. So, in addressing energy, we need to think holistically. So there's an argument this morning about a question about what's the best solution, what's the best technology. That's the worst question you can ever ask. There isn't a single answer. And it's how we put these answers together. Now, that's really important. So electricity, certainly in Scotland, is pretty much fixed. We produce more renewable electricity than we use. We've got a battery called England, which is quite helpful. But you want to translate energy into transport, into chemicals, and then you want to manage the system to manage the heat. So it's between where I live in St Andrews along the coast. Some nice geology. This is about New Year's Day at lunchtime. So you can see from the length of the shadow we're peak day. That doesn't quite look like that. Now, if you look closely, you'll see a lot of windmills. And there are now 3.4 gigawatts, which is about the electricity needs of Scotland. So it's quite significant just from these wind farms. Neil Dungur, that you can see from home, is 700. And Seagreen, that I'm going to mention later, just shortly, is another gigawatt of offshore wind. Scotland is already 100% sustainable electricity. So there's an argument about what price is hydrogen this morning. When I spoke to Scottish Power, I asked them what price was their electricity. And they said negative. They've spent $1 billion in the last couple of years switching off electricity. So if you can combine the renewables with the hydrogen production or with other chemical processes, then the price is there. You can't afford to buy renewables and put a cable, well, They want to put a cable down to London from we are. $1 million a kilometre. You spent that, you're not going to do anything else with it. So we need to be selling these technologies now. Hydrogen production, we can't do gigawatts. We can't. You know, that's what we need to do, is to be able to produce hydrogen more cheaply. Don't worry about what BOC will try and sell the hydrogen at. They're making a short-term gain, and I can't understand why they're not selling hydrogen at lower value, because people will use more hydrogen and everything will grow. They're not looking at the future. Sea Green is now up and running. The blue is what's been curtailed in the last couple of years. So more electricity has been curtailed, i.e. the wind farm has been switched off than has been used. So there are renewables out there. They're not everywhere's got them, but that's coming, and it's, if we go for it, it's there. CO2 is being produced here at the cement works. There's also a nuclear power station here as well, across the Forth. Now, what's happening in Fife? Grangemouth, the petrol refinery, has been decommissioned. Our government's looking to ways of using biomass CO2 conversion into replacing that. Now, the enthusiasm is there, but they're not really going for it. They've got to go for it. This week, as already mentioned, Mossmoran, 40-year-old ethylene production plant, ExxonMobil are laying that off. So that's all the chemicals buildings. Now our chemistry department was close to being the highest fire risk in the county. Now it definitely will be. We haven't. So what about CO2 electrolysis? You can actually convert using solid oxide electrolysis. You can produce hydrogen from steam, but you can also convert CO2, and you can. Talbot Topsoe have been selling systems to convert CO2 into carbon monoxide. Really, from the convenience and the safety in the US, you can get carbon monoxide in demand if you've got CO2, and they've been selling this here. You can use thermal energy, so you can get very high efficiency. Essentially, you can run all thermally. The system is self-sustaining if you manage it properly. Then you can take solid oxide electrolysis, and you can use that to convert co-electrolysis. You can produce syngas, carbon monoxide, and hydrogen at high temperatures. That's all you're going to get. Then you can convert that into chemicals or fuels. So within ecolefins, we're looking at what would be a clever modification. So rather than having a proton conductor or an oxide conductor, we're looking to have both. And mechanically, that means you can pull oxygen away from the zone, and you can feed hydrogen into it. So it means electrochemically you can modify the catalysis. So if we can do this, and it's quite a challenge, it's got huge potential, and we're targeting ecolefins. So looking at some of the first work, we had a visiting PhD student from China, Qi, who is now a professor, and you'll see more of his results later on, but he looked at direct methane production. So first of all, with an oxide ion conductor, now he used iron and oxide layer to bridge from 650 to 300, because the products we produce in solid oxide electrolysis will often decompose. And through that, he was able to get CO2 conversion, steam conversion, and it produced about 2.8% of methane, mostly carbon monoxide and hydrogen. But you can produce methane at a solid oxide, electrolyte, and electrolysis. If you go to a proton conductor, similar sort of experiment, you get more methane, and a lot of carbon monoxide. So the process changes. You reduce the steam to hydrogen. You actually end up promoting the carbon monoxide. So it's often felt that to do CO2 conversion in co-electrolysis, you produce hydrogen, which then reacts with CO2. But in certain systems, you can do the CO2 directly. In this case, it seems preferable. Now, looking back at some of our previous work on proton conductors, we were trying to determine the stability of these materials in CO2 under reducing conditions, because we know that barium material is not stable under CO2. And we did some TGA, and weirdly, we found lots of carbon monoxide, as we have here. So you've got high conversion of high water gas shift just over the proton conductor. So the electrolyte is itself a catalyst, and that's why it affects the conversion. So he completed his PhD, went back, and we spent some years collaborating on CO2 conversions. And one of the things he was looking at was using X-solution materials. So this is something that we developed, we've let loose in the world, and most of the stuff is not very good, actually. It's rather disappointing. It's not a magic thing. X-solution is decomposition. And we've all, as a chemist, I've been making lots of phases that decompose for many years. So X-solution is one phase, one of the two phases. Sometimes it works very nicely. You have to think about that. So this is from geology. It's feldspars under cooling. They separate from one to another. Redox X-solutions, we use reduction to drive that. And we would say that thermodynamic driving force is really important. If there's a strong driving force, you don't get subtle structures. If it's close to equilibrium, you can get some very stable, very subtle structures. So here you have grains of manganese, iron, chromium, spinel. This has been strongly reduced and exudes metal particles. So you can see the original grains are still there. And these may be quite good catalyst supports. But that happens with the iron being produced and the iron exuding as a metal. Intermediate, we'll see an example of nickel manganese oxide. You've got larger particles that are sitting on the surface. They're exolved, but it's really a composite. And it might be a fairly stable composite, but just because you form a composite doesn't mean it's going to be good. And then we call the emergent materials, which I'll say a bit more about. You get this very fine structure, 15 nanometer particles, 10, 20 nanometers apart. So really almost breaking the laws of physics and chemistry. You'd expect osmolar ripening here. So the trick that we do is often we have A-site deficiency. So rather than forming three phases on X-solution, you produce your metal and you form a perovskite that's closer to pure perovskite. So you start with an A-site deficient perovskite. Another way of looking at that is you take strontium titanate, you replace strontium with lanthanum and introduce metal cation vacancies on the A-site. Then reduce that, remove oxygen, and you now have two sites in the lattice that are empty. That destabilizes the third site, and you have, say, nickel 2+ that migrates to the surface, and it's reduced at the surface. And this is the kind of thing that you get. This is a cleaved surface, a really neat X-solution, very well supported nanoparticles. And the key thing is these can be really stable, so you can get durability from that. So 6% nickel, 20% deficiency on the A-site. And you can see that even up to the cleaved surface is pure perovskite, whereas the native surface is a little bit strontium rich. So as you expect in perovskites, so you get the X-solution on one surface, not the other. And the particles are not on the surface, they're sitting in the surface. So they're actually in a pit. And if you dissolve them with acid, you find pits behind. And then something that's quite weird is the unit cell parameter. The exolved particles got similar lattice, the cubic lattice to the perovskite, but the unit cell is 10% different. You wouldn't expect epitaxial X-solution or epitaxial layer interfaces. That's such a big difference in unit cells. So that's really surprising, but you can see that the lattices are consistent. They go across. And so there's a lot of chemical and physical strain there, which is again probably why it's so stable. And then looking at hydrogen production. There's Jeha and Dragos. This work on calcium, lanthanum calcium titanate, doped nickel. We made first time a non-ceramic electrode, so pure perovskite that's been reduced to produce nickel nanoparticles. If you look at the crystal structure, materials processing is very important for what we do. So you need very nice interfaces, good crystals, but you can see very nice nanoparticles by chemical reduction. If you apply 2 volts without reducing it in a non-reducing atmosphere, you get even more nanoparticles. That's what we call electrochemical switching. So the reduction took overnight at 900. The switching is in 50% steam, 50% nitrogen. That just took a couple of minutes. So electrochemistry is very powerful. Applying 2 volts is quite significant. So you can redrive these processes. And then that worked really well as for steam hydrogen production. Getting 3 amps per square centimeter is pretty much state of the art for solid oxides. And for people, what the company people would have said was impossible, it's very pleasing after a number of years to show that we can actually make new materials that work like repeat. If you just work out what the Nernst potential is for 2 volts, it tells you the oxygen partial pressure is 10 to the minus 35. Now, there are stray voltages, that's not exactly, but it gives you an order of magnitude. So it's much more reducing than the chemical additions. Now, one of the key things about these pitted particles is here you have deposited, and here you have exolved nickel. These have been in 20% methane 800, and you get lots of nanofibers and totally destroyed electrode in this system. But with the exolved particles, there's very little carbon deposition, and what there is basal growth. So you maintain your electrode structure. So these look like good candidates for CO2 electrolysis, and here you have using 2 volts, 2.2 volts to drive the process. You get a big reduction in the electrochemical resistances, and you produce quite an effective electrode. So here you have nanoparticles, and you're doing the electrolysis in pure CO2. There's no safe gas. You can't do that with a nickel YZ electrode, and you get conversion of CO2. So I mentioned redox exolution before. Just because something isn't A-site efficient and beautiful doesn't mean it's not going to work. So looking at this one in particular, nickel exolved from manganese oxide. We worked on this. Here you have these nanoparticles from large, well, sub-micron particles. They're 100 nanometers. You have a very strong interface. But the key thing is that I would like to highlight is the nickel is here. Having manganese and nickel really works. And you find that manganese and manganese oxygen vacancies enhance the CO2 absorption. So having manganese in the structure improves the CO2 conversion. So manganese and exsolution are important. Another magic ingredient for CO2 is cerium. So cerium oxide and manganese are 2 particularly good systems. So this is cerium oxide that's got nickel copper inside. It's evolved that, and again you find the enhancement in the conversion at this cerium system. So going back to A-site deficiency solution, we looked at various compositions. These are 95% dense. This is manganese nickel. This is chromium nickel. These are non-deficient, which are effectively oxygen excess, and we compared these materials. And here again, you get very good CO2 conversion. The one that works best is what we would like to work best, the manganese containing A site deficiency. Then the chromium condition. So the A site deficiency makes the X solution much easier, makes the sample easier to reduce, and you get better performance. So to right, you get high carbon monoxide reduction from these systems. And again, if we look at temperature program reduction, you see the sample with the best performance has got the strongest CO2 absorption. So absorbing the CO2 at the surface is key. And again, in the Raman, you see that the peaks are much enhanced with manganese. So summarizing all this, we can facilitate CO2 electrolysis by surface control. Nickel emergence is beneficial. Manganese surface with oxygen vacancies nearby is useful. Cerium is ideal, and if you're making a commercial type system, you might well infiltrate cerium oxide or a cerium oxide on top of the A site deficient perovskite. So let's make things a little bit more complicated. Let's look at biogas. So, we're looking to enhance biogas properties. Biogas is an important, as we mentioned earlier, there's a lot of biogas produced in Europe. And Northern Ireland, where I come from, there's far too much biogas produced. And electricity companies are paying people to produce electricity from biogas, come what may. And if they stop producing it, they get penalised. That means there's huge nitrate effluents in the locks, and that's causing a lot of environmental problems because they're producing more electricity than they need, and not able to switch it off because the companies will penalise them if they don't provide supply. So they end up with lots of nitrates, and that has to escape, and that's caused a lot of problems. If you could use biogas for synthesizing chemicals, as we've talked about today, Fischer-Tropsch, you can produce chemicals and fuels. Biogas is well used in India. This is a small dairy we visited some years ago. It's a biogas plant. A lot of cooking is done with very primitive biogas systems, and this uses a 100-year-old Lister engine with probably about 10% conversion efficiency to produce electricity. But that's used on a cooperative farm in India. So it's about 60% methane, 40% CO2. And the problem with that is it's not the energy intensity is not sufficient. It's hard to burn it. If you have a bit less CO2, you then have a very attractive fuel, and that's what we're trying to do. When you can transform the biogas, you get steam, carbon monoxide, and hydrogen produced when you reform it or do gas shifts on it. There's a whole range of reactions that can occur. Now, as a scientist, you'd like to feed in a gas mix, and you assume that's what's there. But by the time your gas mix reaches your fuel cell or your catalyst at 500, it's not the same things you put in. So you have a range of reactions. Important parameters are the carbon, hydrogen, oxygen ratio. You want to avoid carbon formation, and at higher temperatures there's less coking. So you can avoid coking by going to higher temperatures or adding more oxygen through carbon dioxide or steam. So this is 50% CO2, 50% methane, and you can see that there's no carbon decomposition above 700. And the gas compositions change a lot as you increase temperature because you have a lot of contributing reactions. So when we fed CO2 and methane into there's a nickel YSZ fuel cell, conventional electrode, lanthanum strontium manganese air electrode, and we fed nickel so CO2 methane mixes into that. And you can see, first of all, that the carbon monoxide production increases as we apply current, increase the voltage, more current, more CO conversion. So the gas composition changes. Doesn't start off at equilibrium. So the initial gas composition is somewhere between what we feed in and what would be full equilibrium, because we're using an electrode, not a very finely divided catalyst. In terms of conversion, you can see that the 60% methane, 40% CO2 has the lowest current and has this degradation. Whereas the other two compositions that are richer in methane are richer in CO2, so less useful as a fuel, but are more stable. And then looking at after electrolysis, you can see the structures. And if you look in more detail, you can see why the degradation is coming there. We didn't see any carbon, but we see oxygen where there shouldn't be oxygen. So you end up with a very spongy nickel oxide on top of the nickel. So the nickel is reforming, restructuring onto the gases. So you don't end up with carbon when you analyze it at room temperature, but you do see the electrodes badly degraded. And that's often what you see in these systems. You see nickel migration, nickel reorganization. So it works on the nickel, but you have stability issues. We're trying to develop electrodes that are more stable, and Nushi has done a lot of nice work on this system with different metals replaced titanium. So 5% manganese, 5% nickel is typical. So well, the initial performance in the first experiment she did was not quite as good to start with. It was stable. We didn't. So this is with the LCNT, the ozone nickel oxide. So initially you've got a stable system. If you put manganese into the titanate, you see that when you reduce it, it reduces much quicker. Manganese promotes oxygen transport. Without manganese, it's quite slow. The conductivity change as you reduce is much more marked with the nickel and manganese, even though the manganese doesn't help the initial conductivity on reducing conditions. So manganese makes nickel easier to reduce, and then you get quite nice, or very nice nanoparticles. So the nanoparticles are nickel, not nickel manganese, and they're sitting on the surface. And stability is long-term as stable as you can get without your colleagues switching off the gas line, basically. So Nishi was not pleased when the gas line was switched off on this experiment. Again, you're running in pure CO2, so you don't pre-reduce the electrode. You reduce it electrochemically, and you have you don't have to protect it. And after from the SEM, again, you see it's stable. Now, this is a very busy slide, so I'll just take a little bit of time on this. So this is before any current is passed. So this is just a catalytic conversion. The amount of CO2 converted without nickel is 20%. That increases to over 30%. So the electrode is catalyzing the conversion. So what you see at the electrode will depend on what the electrode is. But the one on the right shows that as you increase current, you increase voltage, you are converting CO2 into carbon monoxide and methane, actually, and some hydrogen. So the gas becomes more calorific. It's got more carbon content. So with the nickel, it's better and better. With cobalt, it's not quite so good. But actually, if you look at the black, the bottom, that's got no nickel nor cobalt. So no reducible transition metal, only titanium. And if you reduce titanium hard enough, you get enough oxygen vacancies of the perovskite works without the exclusion. So the substrate is clearly becoming more active. And people will often say you need transition metals to be reduced, but actually, if you can get enough oxygen vacancies and enough titanium 3+, the strontium titanate works perfectly well and better than the cobalt in these cases. So, summarize here, we can do direct CO2 electrolysis. We can enhance this with nickel immersion, and manganese is very useful. And we can apply electrochemical switching. Although if you've got a really good system and you apply electrochemical switching, it's worse. Just, again, the students get disappointed if it doesn't improve. And the last thing I want to talk about is our current ecolifference, which is why I'm here, and we're building up a study. Great thanks to George and my colleagues here. So some of the work we've been doing in St Andrews, really been focusing on the mixed conduction. How do you get protons and oxides both moving? And you can do that with a protoconducting electrolyte. So obviously you're using this to remove oxygen and produce hydrogen to improve the electrochemical catalysis. So we've looked at scandium in particular. Scandium is recent mining changes and our search for rare earths that don't come from China. Scandium is now much less expensive than it was, probably 10 times less than it was 5-10 years ago. Depends what deal Trump does with Ukraine, but maybe scandium will be coming from Ukraine as well. There's certainly a good. Well, we used to get our scandium from Ukraine 10 years ago. But as you add scandium, you get more water absorption, you get more proton conduction. So scandium is quite beneficial. It can give us more mixed conduction than yttrium. Question always be asked about barium perovskites is stability. So you can see the one in black, which has got the highest cerium content, forms barium carbonate. It's very simple thermodynamics. If the thermodynamic driving force is to form the carbonate, it will do it. If you replace cerium with zirconium, the thermodynamics become less favorable. Scandium also is a small ion. So you can easily move to the situation like you have with the green and the blue, where there's no uptake of CO2, just an exchange of small reversible change. How do you measure transport number? There's a lot of things happening. There's oxygen ions moving. There's holes moving. There's protons moving, and you have to look at look at very different scenarios. So you have to just control the electrodes, controlling the water content, the oxygen content, and the hydrogen content. And by doing that, you can extract mixed conduction under oxidizing and reducing conditions. So the materials we're looking at here, these are proton transport numbers, about 80% in reducing conditions. Oxygen transport, best samples are giving us about 20%. So 4-to-1 ratio is quite acceptable. So on reducing conditions, total transport number is quite high. Under oxidizing conditions, you get more hole conductivity. So you can lose quite a lot of conductivity under oxidizing conditions. So you have protons, you have oxygens, and holes. So you don't want to go to too high a temperature in this situation. Then transport number is an indicator. It's difficult to get to really look at a full cell. So then we're doing measurement of hydrogen transport directly. So measuring the hydrogen produced, because that's the best way to look at that, and getting the Faraday efficiency from that. And then similarly, you can do that. Then, sorry, here we have the results here. Again, you're getting about 80% efficiency. It's higher At lower temperatures, you're getting 90% at the lower temperature at 500. And for oxygen, so if you look at the electrochemical response, it's very simple. Electrodes work well. So the estimations of the transport number electrochemically are quite good that way. If you go to oxidizing conditions, the electrodes are less well behaved, so you have to be quite careful about the transport numbers. But measuring the gas that transmits, you can see again about 20% transport number of the best samples for oxygen. So we've got compositions that we can take forward, and that's going into the next stage of the project. So we've got an electrolyte. Here we have one alternative for the anode. So we've got lanthanum strontium cobalt ferrite coating perovskite. You can see it's a nice coating. And then here's a copper X solution from a typical barium serum zirconate. So these are our nanoparticles that we can take forward. And the next stages are to go and produce some olefins or produce something. So thank you for your attention. And actually, I forgot to thank the UK government, who actually, because we're not allowed to be funded by, at this stage, we're not allowed to be funded by the European Union, so the UK government funded us. And we didn't have to complete the same number of reports. So actually, we got the money without the burdens, but we're closer to Europe now, so we've got to do the reporting in future projects as a full partner.
Thank you very much for the presentation. We were also happy with the UK government because otherwise all the projects should remove all the partners. Luckily, they cover the cost. Questions? Question? Yeah.
Thank you for the presentation, Professor Irvine. I have this question about these nanoparticles that comes out of the perovskite and sit on the surface and seem so active. Are there any efforts or any schedule for the future to obtain nanoparticles of not just one metal, but of mixed metallic nanoparticles? Let's say nickel and copper in the same nanoparticle, or cobalt and iron. That would be very interesting for ecologists.
Cobalt and iron is okay. We can do that. Cobalt nickel is really interesting because you actually oxidize that and form a cobalt nickel spinel nanoparticles. So we've used that as an air cleanup catalyst on systems. But yes, you can do that. Anything that's dissolvable. Copper is a bit strange and it doesn't dissolve that easily. You'd think copper would be really easy to reduce, but in the tight knit lattice, it's quite stable. But yes, there's lots of alloys going out producing at the moment, and interesting shapes. And
bimetallic, it's nanoparticle to be bimetallic. No?
We've got copper nickel bimetallic, nickel cobalt alloy, platinum cobalt alloys. Quite a range.
Still have only one year left. We have only 1 year left in this project.
Okay.
We plan to continue.
Yeah. Yes, I'm coming there.
Sure. Thank you for the presentation. I have a question about X solution, if it's reversible. And another question is how those nanoparticles change this famous triple phase boundary.
Yeah, good questions. Is it reversible? Well, people always say it is, but they don't actually look. If you do TGA, it takes 10 hours to reduce the samples at 900. You reoxidize, it reoxidizes at 400, except for nickel. So it's forming nickel oxide nanoparticles. And I think that's much more interesting than being able to reinforce. If you heat it up to 1200 degree incorporates and forms a single phase again. But it's what we call chemistry at point. So you actually form oxide nanoparticles. We form cadmium sulfide nanoparticles for photocatalysis. You can do chemistry, a lot of interesting chemistry on those nanoparticles. And when you oxidize and reduce, you reform the interfaces. So you clean up the interfaces. You don't have to dissolve them back in. You can dissolve them, be heat them hard enough. But it's much more fun, much more interesting to change the chemistry and then reverse the chemistry. That's very interesting. So the other question was about, those interfaces made between the nanoparticle and the substrate may actually be more active than the nanoparticles. So it may not be the nanoparticles that give enhanced activity. They certainly give ability and durability, but the interface is very strained. If you saw it, you notice the high resolution image. Those lattices are very discontinuous. If you make the particles too large, you lose that softening. So you need about 10 nanometers for a base metal. Platinum group metals will be stable at smaller. But if it's too small for nickel, you get agglomeration and you lose it. So you need about 10 nanometers. Less than that doesn't give you the. So there's a very strong interaction in the surface. And the triple phase boundaries have to be changing a lot.
Okay, can you do later? Because we have to split now. So thank you, the speaker again. And we also have a big nanoparticle as a present. Thank you very much.
Christmas.
Yes.